Hey, welcome back. So we're going to take a look at a Jupyter notebook, which will of course be up on Canvas for you to play with. Now, one of the things about this notebook is that I'm going to be covering, uh, the same things we just talked about in the presentation, but I'm going to be showing them to you in Scikit-Learn language. All right. Now, hint, hint, this notebook is probably going to form a strong basis for the work you're doing in the final project. And the exact nature of it may be helpful for you in a start, but you're probably going to have to tweak it in one way or another to get your job done. Now, more generally, I want you to start to realize why Scikit-Learn is what we're presenting as the basic tool of the class. It is a highly reusable system. You can not just use, okay, here's a piece of code that's going to let me do support vector machines without me, having to write it. That's great. But what's more to the point is that it's a system for doing machine learning. And there's a lot of ways to do machine learning algorithms, right? Every algorithm has its own loss function. Okay, well, we code that up and we figure out the optimizer for it, and that's the algorithm. But in the same way that that optimization framework establishes the algorithm, right, and how it finds the right solution, there's another framework around it, which we've just talked about, model selection. And model selection or feature selection or hyperparameter selection, they're all fundamental to machine learning. Okay? And there is a system, just like the optimization framework that we've just talked about. And having a system of, easy to plug in software where you can do that same task over and over again with different algorithms or different data in a very easy way, right? You can see how that's most of the battle with machine learning. Okay, so that's what Scikit-Learn gives us, is a lot of tools that make machine learning easier, not just algorithms. Let's get into it instead of me blah, 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 blah. Okay, so, right, we've already talked about this, that there's, up to this point in the class, we've had this basic idea of we're going to choose things. We're going to choose the features of the data. We're going to choose the algorithm. We're going to choose the hyperparameters. And then when all is done, our job is mathematically just train the algorithm on the data, right? Well, as I said, I'm throwing out to you that there is this other thing to machine learning, this method whereby you can automatically find from a number of different possible choices of hyperparameter or algorithm class or ways to re-represent the data, right? That you can keep, oh, yay! Just a little too slow. All right, so thanks, Google. I'm back. It's okay. So we can use this framework for many different things. All right, so let's go ahead and run this since we just disconnected. So I'm going to make use of a few bits and bobs of Scikit-Learn that we haven't seen yet. Okay, a critical one is a pipeline. So a pipeline lets you put together lots of different objects. So quite typically we have to do things like we did in the polynomial version of OLS regression, right? Where we take data coming in and we transform it somehow. We turn it into a polynomial representation, right? And then we apply linear regression to that transformed data. That is super common. So rather than having to write a for loop every single time that has your own particular rearrangement of things in it, because we have the Scikit-Learn framework where we're just going to pass in, oh, here's my estimator, right? Please do this to it. and it's a very simple one-line run. In order to do that, we need to be able to pack many steps into a single estimator, and that's what a pipeline does. It lets us package together the polynomial feature transformation with the linear regression. Okay, so we need one of those. So at this point, we can redo something that you're kind of used to seeing, which is we can have different orders of polynomial fitting, in this case, an asymptotic curve. Okay, so you can see that the orange there is the linear regressor at degree 1, and the 12th order regressor is the wiggly red line, and that green line, which basically for most of it follows right on top of the true value, is a degree 3 polynomial. So we see the same thing, an underfit line, an overfit 12th order poly, and our halfway decent, third order model. So we've already seen in previous goes something like this. This is the not scikit-learn way to write this, right? This is the, we're going to make a for loop. And inside that for loop, and previously what we had done is we had done separate linear model fit and, separate polynomial transform, and then a separate linear model fit, and then blah-de-blah-de-blah. Now that we've got this, pipeline thing, we've just saved ourselves a couple of steps here, and now we just have to fit the polynomial transform. So what comes out of this, right, is we go into that loop, we run over 5 folds of the data, and each fold is, of course, a separate chunk of the data with no overlap between them. And we can find that the mean squared error is this over the whole set of data, right? And on each individual fold, these are the values. And you'll see that some of those values are bigger than the mean, some of them are smaller, right? And then there's this mean. Okay, so you get the idea that each fold has some variability, just like we were talking about. And the more folds you get, the higher the standard deviation is going to be among these. That's the kind of variability that we mean. All right, but as I said, this is not the scikit-learn way to do things, because scikit-learn, of course, allows you to do it much easier than that. You don't have to write a for loop. If you've packaged it all up into one unit, you can just call, hey, get me a cross-validation score, please. And you'll see there that we get the same answer, right, here and here. Okay, of note here is that we can call this with any kind of metric we want. Okay, Scikit-learn has a nice list of metrics for you, which include all the things we've discussed in class: R squared, mean squared error, mean absolute error, precision, recall, and a whole bunch of other things you've never heard of yet. Okay, so all we have to do is we have to take one of these metrics and turn it into a scorer class, and then we can just we can do a cross-validation, and to evaluate it, we'll use whichever metric we feel like. Okay, so this gets you an idea how we can go from the last notebook we did in logistic regression, right, which, oh, thanks, of course, right, where the cross-validation, wherever that went, was it in here? No, it wasn't in this one. It was this one, right, where we have to do this 5-fold split and rerun this every time, and inside that 5-fold split would be multiple steps like this. Okay, and we've just sucked that all down into 2 lines of code. So that's nice. And obviously, we can do a whole bunch of different kinds of algorithms this way. So it's 2 lines forever, right? And all we have to do is just build a different pipeline to make a different kind of classifier. or regressor in this case. All right, well, not just that. We can go ahead and get ourselves some fancy visualizations. So the validation curve is a way to check lots of different hyperparameter settings, okay, and do it in a visual sort of way. So what we do is we have our packaged up pipeline, and we're going to do 5-fold cross-validation on it. We're going to score using the R-squared metric, okay? And what we're going to do is we're going to use these 5 folds of cross-validation to investigate what happens when we change the degree from, 1 to 2 to 3 to 4, all the way up to 15. Okay? The way this works is we just have to know the name of a parameter inside the class of the pipeline we made. Okay, and once we have that name, we can give it a range of values here. So in this case, it's just the values 0 to 15. Right, so when we run that, what we get coming out is a train score and validation score. So maybe I should make that super clear, right? What does train score look like? So train score is an array, and this is the training error, okay, which starts out at 0 for a 0th order thing, and very quickly heads up into a fair number of, 0.66 to 0.9, right? And you can see that curve right there. And each position in the train score matches each position in this degree vector. So this is probably actually a little bit too much level of information, but just to give you an understanding of what's going on here. Okay, so we can see as we vary the degree, what happens? Well, the training score goes towards perfect, right? And the validation score goes up, up, up until we get to a reasonable level of fit. And then we are overfitting and we go down, down, down. We are no longer doing as well in the validation set as we were before. And again, the validation set is just when we do k-folds, we hold out, so it's a 5-fold, we're going to hold out 1/5 of the data. We're going to train on 4/5 of it, and the validation set is that holdout 1/5. And we do that 5 times, and we average across those 5. And we do that in parallel, in this case for 15 different model hyperparameters, 0 to 15 on the degree. Okay, and we can see here which ones are the best choice, because we know that training score becomes perfect because we're overfit on the data, but validation score gives us an idea that somewhere in here is probably what we want. Okay? So I've actually already given away a bunch of the answers to the pop quiz here, but when you investigate this yourself, I would like you to think about these things. One thing that you need to think about is this. What is that score? Do you remember? Bueller, anyone? Yeah, it's R-squared. R-squared is very typically something that we use for regressions, okay? It's also called explained variance. It's how much of the y is explained by the changes in x. And it is also related to the correlation coefficient, right? So R-squared, when R-squared is close to 1, we have something approaching all the dots lying underneath the curve you're fitting. So that's great, and you can choose other ones, right? So, all right. Now, one other thing you might like to do, so the validation curve lets you look for one hyperparameter, one change of model, okay? And it doesn't have to be a hyperparameter. It could also be different, you know, formulations of the features, okay? But for one of those, what happens to the validation error? That's what the validation curve gets you. But another thing you might like to know is, how does our performance change in the validation set as we change how much data is available? Okay? This is a kind of analysis that you might want to know about, like, oh, could I make this better by doing another month worth of data collection? Is that going to change things? Or is another month's worth of data collection not likely to make any difference in my performance? You might also want to know, you know, is this learning algorithm I'm using just too powerful? Or is it only too powerful given that I have very limited data? And so it's easy to fit the noise. So to address those questions, we can do a learning curve. We can get, instead of the 15 data points we had before, we can get 50 new data points drawn from the same underlying distribution. Okay? And now we can do our cross-validation so that what we're doing is we're pulling out in each cross-validation fold, we're going to use a random subset of the training data. So we're going to pick 15 values out of all the available training data, which is a lot more than 15, right? So we have 4/5 of the data in our 4 other folds, so we have up to 40. Okay? So in 10, 15, so on and so forth, what do we get as an average across all the 5 folds of the cross-validation? What does our validation error look like? So our training error is always quite good. Our training R-squared is always hovering in that 0.8 to 0.9 range, no matter what. Okay? We can always fit the data we have, but we're not going to get an accurate picture because we're getting a small random subsample at 10 training data. We're going to maybe, you know, pick off a few of these data points, but not all of them that we're seeing that 50. Okay. So degree 2 polynomial, you can see that that red curve goes up. That's the left-hand side there. That red curve goes up reasonably quickly. By 20-ish, we're doing pretty good. But in degree 9, it looks like you need over 30 samples out of 50 to get a reasonable estimate of the true underlying thing. Okay? So we can see that it's not so much that degree 9 is always going to overfit, but degree 9 is going to always overfit if we have small numbers of training data. All right. So we've already covered the idea of nested cross-validation. And remember that it's about the fact that cross-validation is kind of a good enough thing. We know we're going to get a pretty good estimate of which hyperparameters are best using it. But if we don't have very much data, or we want to make sure, you know, as best we can to see if we really have state-of-the-art performance with our new algorithm, or if it's all just lies and random rolls of the dice, right? Then we want to get the most unbiased estimate we possibly can of generalization performance. Sorry, not generalization performance, of validation performance, of which one of these parameter settings truly is best. Okay? So this is a method where we, as I said, just do inside each fold of the training data in a cross-validation, we do another cross-validation. And here's an implementation. Okay? There's nothing too hard here to understand. It just has, we're going to do a bunch of trials. Okay? And so we're going to do this over and over and over again. We're going to make multiple nested cross-validations, because I want to show you how much better k-folds could be, nested k-folds can be than regular k-folds. So we just make 2 cross-validators, and we're going to do a grid search on one of them. Okay, and on the other one, we're going to run a cross-val score. And important to note is that the okay, so let me just go ahead and run this. Oh yeah, this takes about 20 seconds, which is why I was realizing I had to stop here and get it going. So so what you see here is this, right? So this is a grid search where we're going to find the best winner of all the different model parameters that we're trying, right? This p-grid has a list of all the things we're going to check and all the parameters we're going to check. So, but if we run that inner, right, so that the result of this grid search, the best one in the inner side, is going to become is going to get cross-validated on the outer side using this method. Okay? So here, this is what happens. What you're seeing is, again, we're doing this 20 times. We're going to redo a particular classification task. And in that classification task, redoing it 20 times with 20 slightly different data sets, right? What we get is each trial we get this red line with regular old cross-validation. This is our estimate of accuracy, classifier accuracy. 86% of our predictions were right predictions. Okay, and you can see blue is the nested version of that. The nested version is always a little bit lower. In general, the difference between the non-nested and the nested is always a positive number. Okay, the average difference there is approaching 1% of the score. Okay, so on average, we're seeing that the nested version is predicting a validation performance about 1% lower. Right. So again, that is the most unbiased possible estimate. All right, let's flip. Let's do one totally different thing. This is, we might find out, so we were using the penguin data up here, by the way. If you remember our penguin data set, the measurements of bills and so forth, and flipper length. There were 3 different penguin species. And one of them we have significantly less of than the other 2. So the chin straps, like if we were doing cross-validation, regular old cross-validation, where we're just randomly throwing each data point into whichever bin, random effects, we might end up with a case where like there's only a couple of these chin strap penguins in a given bin. And maybe they're all, female. So if you train on that setup, then you're going to maybe get a really bad validation error, okay? Because you've never seen any male chin straps and only a few chin straps in general. All right, so the solution to this is to use a k-fold, which tries to make sure that every fold has the same proportion of classes in it as the overall training data do. How does that work? Well, so if this is along this x-axis on this stratified k-fold figure, if these are the classes, these are the chin straps on the left in blue, and then the is it the Adelies and then the Gen 2s and then the Adelies in the peach and the brown color, right? So this is what all of our data looks like for these several hundred penguins. Well, what we're going to try to do on each fold is we're going to try to sample some of the Adelies, some of the chin straps on the left, some of the Adelies in the middle, and some of the Gen 2s on the right. And so look at that 0 row here, right? You can see the blue is the training stuff, and the red is the validation stuff. So line that up with the classes in this figure, and you'll get an idea of what we're talking about here. So this 4-fold stratified cross-validation is keeping a constant amount of Gen 2's, Adelies, and chin straps in each one of the folds of it. Okay, take a look, study that if it wasn't clear. So let's see what happens when we do penguin training with a logistic regression trying to predict species, given those measurements of bills and flippers and so on. Okay, so we're going to do it 2 times. We're going to do a cross-validation with logistic regression, which is just a regular old k-fold. And we're going to do one where we run a stratified k-fold. What is going to happen? Well, so we're going to do 10 folds. And so what we see here in the table is for each one of those folds, what's the performance level on the validation set? Well, it kind of by eye looks like the numbers on the right in the stratified are a little bit higher, but let's go ahead and calculate. So the mean value in the regular is 97% accuracy. On the right, it's getting almost to 99% accuracy. You can see that the standard deviation is half from fold to fold of what it is on the regular, right? Because what's happening is roll of the dice, some of those folds don't come up with as much chin straps, right? Just like we were talking about. So as long as you think that your data set is a representative sample of the true population, in general, you should use stratified k-fold whenever possible. Okay? But you should especially use it if your classes are not balanced and you think that your sample is a true representation, right? So if you're trying to classify cancer or not cancer, then your data set better have just as many healthies as the real population does, and just as many cancer patients as the real population does in proportion. All right, and in that case, then you should probably train your classifier with a stratified k-fold. All right, finally, let's just really quickly burn through this piece of code, which will help you do model selection. Okay? The model selection code here is a little complicated, but let me just give you a vague idea of what's going on. Okay, we're building a pipeline, and that in that pipeline, we are putting in a scaler to rescale the data and a classifier. We can tell grid search to not just search different hyperparameters, but we can actually change the entire classifier entry. We can run logistic regression in part of this instead of just random forest classifier. So if we're trying to try different algorithms, this is one way you can do it. Okay, I'm going to show you one more way. And actually, that was the way I didn't want to show you. This one's even better. It's the same kind of idea. We can create, if we're going to do 3 different classifiers, we can create 3 different ones of those. We can make 3 different pipelines. We can make 3 separate parameter grids. And then we can make a loop, an outer loop. Okay, why did I say that's even better? Because I've generally preferred the the approach where we one-liner it, right? Scikit-learn, let's use all these convenience functions. Well, the cool thing about this is that we can create a our own understanding. Okay, we can look at the training as it happens. We can see what levels it's at in the middle. We can get coming out of it, we can easily control what we're looking for. All right. So I feel like this one's just a little bit more clear because we can, in this case, look at the accuracies directly instead of having to dive deep into the cross-validator method. If you do want to get into a cross-validator, the grid search, once the grid search is done, right, you can just, it's going to tell you what the best one was of the grid search automatically. Okay, so you can get the grid search best classifier. Where is that? Here. Dot best score. Oh, why do you keep redoing me? Where'd it go? Right here. Okay, that's the best score. And similarly, there's best classifier that comes out of these things, right? Best params. Okay. And if you take a finished grid search and just retrain it, it's going to retrain the best version of the grid search. So that's convenient because you can see that right here. We just take the best grid SVM and we fit it. All right. So this is a relatively complex piece of code, and I don't have enough time left to accurately explain it to you. So that's why I'm going to let you play with this yourselves. You'll see that this is a good framework to start to address the project. Okay? And when you want to get into the nitty-gritty, if you want to see how the grid search keeps track of everything that happened during the search, then you can look at CV results here. Okay, this is like next level stuff. If you're going to try to do some of the extra credit things, this information can be very useful to you. All right, people, thank you so much for giving me your time. I think I just want to end, I forgot, with one other thing. All right. So all this stuff, the entire final project is a numbers game. All right. My number, my algorithm's number is better than your algorithm's number. I must be the best. I do want to end by saying that a measurement game is just about as useful sometimes as it sounds like. Okay. There's a reason why it's sometimes called measure baiting. Okay. It can be a difference that you measure which has no effect on the outcome, right? We know that random variation exists. If you get more of this data, would your number one algorithm actually be better than your number two algorithm the next time around? Or would they flip, right? Okay, knowing that there's maybe not much difference between places 1, 2, and 3, okay, in many cases, you might want to think about this, the parsimony principle. If this is your accuracy score, and these error bars here are the standard errors of the performance across the cross-validation folds. Okay, so the mean of the cross-validation performance, right, is, whoops, forgot you probably can't see my pointer. Oh my, let's do this. All right. Sorry about that. So, right, so each one of these dots is the mean of the cross-validation performance, and around it is standard errors. So these are the best performing ones, but what's the true difference between any one of these three, because those error bars are very overlapping. So you can't be sure that there's a true difference, and if you didn't roll the dice again, you wouldn't get a different reordering. So in the case of there's no clear winner, right? That even though this number is higher, do we really want to use the gamma equal to 100? Well, in that case, if there is no clear difference among these, maybe you should pick the one which is the simplest, right? Which decision boundary looks best to you? All three of these are within standard error of each other. No, my bad. This one is not. This one's worse. But these two are within a standard error of each other quite easily. Which one do you think might be more accurate representation of the true boundary? Right? So in cases where everything else is equal, which can happen surprisingly often if you check out these error bars, then generally maybe you should prefer the simplest model, the one that has the easiest decision boundary. Okay? It's a version of Occam's razor. So thank you very much. I hope you all have a lovely, lovely day. Bye.